Alright guys, wait, which one? Huh? What do you mean the day of? We will work on, but what we're going to do is go ahead and work one of them in class. So that means everybody will have at least one done if they remember to bring them in. Or if they show up. Which one y'all want to work?
3.
Number 3?
Yeah.
This Fullway Bridge.
Fullway Bridge.
Everybody got their formula sheets out? Make sure y'all know exactly which formulas we're working with. This is our circuit that we're going to be solving for. So guys, where do we start at? No, I wouldn't start there. I would start with the transformer first and work my way back toward the load, right? So what we do is we'll come over here and we got a 4 to 1. So this is a divider. This is a step down transformer. So I'm gonna calculate the V secondary, and that's going to be equal to 120 divided by 4. What do we got? 30. Are we okay? And then I calculate the peak secondary. So I'm going to say 30 divided by 0.707. What have we got?
42.
Then I calculate V peak out. So I'm going to say 42 minus 1.4. Why 1.4? Because it's a full-way bridge, right?
40.2.
We okay so far? Yes or no? So this is pretty standard on what we've done up till now. I haven't changed anything. Now what we need to do is we need to calculate the DC out. So how are we going to do that? Well, the 2 V peak over the pi and the V peak over pi are gone. Y'all understand that? So what we got to do is we know this output is going to be a ripple voltage. It's going to be a DC with a what we call a ripple voltage riding on top. So what I'm going to calculate is I'm going to calculate the ripple voltage. Here you go, Barry. Here's I think we call it VRPP. I think. I don't remember what the thing is. So what we're going to do is we're going to do what? We're going to use what's the formula? VRPP. We got 2 we can use. Yeah, current divided by frequency times capacitance, right? Are we okay? Okay. So I'm going to say, what's my current? 2 amps. Divided by, what's my frequency? My frequency is 120. Because we're talking about the frequency of the pulsating DC, not the input frequency, right? You'll understand that. Times the size of the capacitor, which is 50,000 microfarads. Pretty good sized capacitor. Probably would be pretty expensive. This is a pretty good power supply. So what's my ripple voltage peak to peak? So down here, you're probably going to have to use parentheses on your calculator, right? You'll need to understand that. Because if you don't use parentheses, you're going to end up dividing 2 by 120 and then multiplying your answer times 5,000. That's not going to give you the right answer. So you need to get used to using, the, parentheses key on your calculator. So I'd say 2 divided by, then what I do, I open parentheses, I'd say 120 times 50,000 times 10 to the minus, this is micro, right, 6. Then I close my parentheses and hit equal. 333 millivolts. Yes or no? Everybody okay? Joey, you're looking kind of, huh? It's minus 6, yeah. So 333 millivolts. And of course, 0.3 don't hardly make any difference here. Millivolts. Now I'm going to calculate my output voltage. My DC output should be approximately equal to V peak out 40.6 minus the ripple voltage 333.3 milli divided by 2. So this is going to be a pretty good unregulated power supply. Well, look at the size of that capacitor. 50,000 microfarads. What we got? It's still gonna be 40 point what? Can't be higher than that. You can't subtract. Oh, okay. I'm sorry. 40, but 40.6 is what we got right here. So. Okay. Yeah, we need to round this to 1 decimal point. So let's go back and correct these. So we're rounding to 1 decimal point, right? Y'all know that means not dropping. 42 point what? 4. And what would that give us right down here? 41.6. Oh, I'm sorry. Good. And the only thing that's going to change down here is just a little bit. What does that give us for our output voltage? $40.8. Is that okay? Yay, no, indifferent. So everything's the same until right about here. And this, we calculate DC out differently because it's never pulsing 0. Right, y'all understand that? Now if you use D ripple peak peak is equal to I times F over C. This is, I mean, not times time over C. Then what you're going to use here is you're going to use 120. You got to know the period for 120, which is 8.3 milliseconds. So to me, it's easier to use this formula because that way you don't have to know the time, right? You understand that? Which makes it a little easier. But you still have to know that the pulsing, the capacitors charging according to this. It's not charging according to that. So a lot of people see that 60 out there and they want to use 60, but full wave, the pulsing frequency is twice the input frequency. Half wave, it is the same, right? Y'all understand that? So that's what you gotta know. We use a parts place called Democo Electronics a lot. They have real good deals. So most of our parts come from there. We'll see what they got available in though. By the way, these capacitors are polarized and they're referred to as electrolytic capacitors. I spelled it right. Yeah, we'll see what they got. Let's just look at capacitors. Huh? Electro. What?
Delete. It popped up when you were.
Oh, it did? Oh, there we go. Electrolytic. Not, I guess bipolarized. It says it's not there and it gave you. So we'll just look for capacitors. They call it. So they come in all shapes and sizes. What we're doing is we're looking for these electrolytic capacitors right there. And of course, the bigger they are, the more they're going to cost, right? So I don't know. Let's look for no results. Okay. So Mauser sells one for it's definitely not it. It says 43 matches for 53,000 microfarad, and then I don't think so. So here it is. So they cost about $58.83 a piece. But we get very, very little ripple, right? You understand that? 33 millivolts of ripple. So, but if we drop the capacitor down, what's going to happen to the ripple? It's going to go up, right? So it all depends on what we need, what we can get by, and what we're going to regulate. So this is a pretty good size capacitor, so and it's not very cheap. So any questions? You okay? We're not going to work another one.
1.4, use that
Not full wave when it's a full wave bridge. Yeah, because any way you pass the current through the thing, it's got to go through two diodes. So when we come up here and look, so if we follow any path through a forward bias screen. So what you would do is you'd come over here and we make this positive and we make this minus. Then current's going to flow out here. Okay, it can't get over there, so it's going to come through there, right? Okay, then what's it going to do? It's going to go out, come up through here, right? And it's trying to get back to the opposite polarity. The difference in potential here, so this guy here's off, so it goes that way and goes back to the positive. Well, how many diodes did we go through? It went through 2. So that's why we subtract 2 diode drops. And we could come over and switch the polarities, and these 2 guys here would cut off, and these 2 guys here would cut on, but it would still give us 2 diodes each time. But no matter which way you go, so I'm going to change the color. Let's go to red. And if we make this, and that way we can leave both of them over, because I want to show you the current flow through the load is the same direction. So if we make this positive, we make this minus, then it's going to leave here. It's going to go down through this one now, right? You understand? It's going to still flow this direction, going up through the resistor in the same direction, and now it would go back to this one and go back to the positive. So no matter what the polarity, is going to flow in the same direction through the load, right? Which is what DC is. But as soon as we add that capacitor, then it's no longer pulsing to 0. So what happens is that even though the pulsating DC is doing this, so this is what we're getting out of our diodes, right? You understand? Well, what happens when the capacitor comes in, what does it do? Well, it charges up instantly. The only thing that's limiting the charge is the resistance of the transformer. Transformer has almost no resistance at all. Okay. And then as soon as it tops out, the diodes cut off because they would be reverse bias, and then the capacitor starts discharging. And then it's charging and discharging, charging and discharging, charging and discharging, charging and discharging, right? And then, of course, now what happens is we lose what? We lose all that. And we get DC. And this is what we call unregulated DC, because I showed y'all what happened. When I put a bigger current load on there, the ripple got bigger. And if the ripple gets bigger, it means the output voltage drops. So we had the multimeter on there, and when I put that other resistor in parallel, which required more current, we actually saw the digital multimeter read less, and of course that was because the ripple got bigger, right? You understand that? So we call this unregulated, which means it's going to vary with loads. Also, it's going to vary with the input. So I plugged this, we did all our calculations around 120 volts. But if your house, you might measure like 110 or something like that. Well, if the input voltage is different on your house, then my output voltage is going to be different, right? So what we're going to do with a regulator is we're going to compensate for different input voltages and also different output loads, which is going to be pretty neat. But they've got to be, your voltages have to be within a tolerance of 120 volts. I think it's 10%, which is the maximum tolerance that the power company allows. So as long as we make sure we get that 10% out of the way, then our regulators will regulate. So we're right here so far. So what do we got? We got our plug, then we got our what? Our transformer, then we got our what? Then we got our rectifier, and then we got our filter. And the next thing we're going to add is this thing we've been talking about called a regulator. And once you figure this out, then you'll be able to build your own power supply at home, which is pretty neat. Whether you want to or not, it would be a pretty neat experience. So any more questions? So you understand why we did the 1.4 now. So full wave bridge, 1.4. All the rest of them is what? 0.7. Any more questions? I don't know what you meant. Oh, if they're forward bias, yeah. Yeah, that comes into play when we do that little tiny circuit with a battery on it, which nobody seems to get. Where I reverse bias that diode. And somebody's gonna miss it next test too. Somebody will miss it on the third test, somebody will miss it on the fourth test, and somebody will miss it on the final. Any more questions? I don't know what's going on. The thing won't go away right there. Anybody got any suggestions, something like that? It usually goes away by itself. Well, but it still usually goes away by itself. I mean, I don't know. Huh?